Don't forget to subscribe and ring that bell.
What an absolutely beautiful day. I have my coffee with my peppermint mocha coffee mate creamer. And we're about to do some calculus. I mean, it doesn't get any better. Welcome back to the 2014 AP Calculus AB practice exam. We are going to cover the last part of section 1, part A. This covers multiple choice numbers 21 through 28. And lordy, lordy, we don't get to use a calculator, but that's fine. We've been good without the calculator for problems 1 through 20. Let's continue. Number 21 reads, functions w, x, and y are differentiable with respect to time and are related by the equation w equals x squared y. If x is decreasing at a constant rate of 1 unit per minute. Ooh, that seems like it's important. So let's start, highlighting some stuff. First of all, w equals x squared y. And x is decreasing at a constant rate of 1 unit per minute. And y is increasing at a constant rate of 4 units per minute. At what rate is w changing with respect to time when x is 6 and y is 20? So I use these different colors here for a reason. There was some intent behind this. First of all, we're going to establish what rate is w changing. I'm going to find w prime. They're actually asking me to figure out what the rate of change or derivative of w is. All right? And they give us w equals x squared y. This is a related rates problem. Anytime I take the derivative of a variable, I need to put dx dy next to it, or excuse me, with respect to time. So I've got to put dx dt next to it. When I take the derivative of a y, I got to put dy dt next to it. All right? You can use the little apostrophe like I use for the w, but I think a lot of kids get confused that might be an exponent of 1. And that bothers me. I really like to write less, but I will do this appropriately. Okay? So, first of all, let's find the derivative of w. So dw dt equals product rule. First times, the second. So the product rule states that it is the first, x squared, times the derivative of the second. The derivative of y is 1. But every time we take the derivative of y, we got to write dy dt. First times derivative of the second, plus the second, just as it is, times the derivative of the first. The derivative of x squared is 2x. And when I take the derivative of an x term, I got to write dx dt. Okay, so we have all this stuff with this nice problem here. This is what we're trying to find. I need to put values into all these variables. And that's what I have underlined in the purple and orange highlighter. So x is 6, y is 20. So x is 6 times, I still don't know dy dt yet, plus y is 20 times 2, again, x is 6 times 6, and I still need dx dt. All right, so we plugged in for our x's and our y's. This one right here. Y is increasing at a constant rate of 4 units per minute. That is telling me dy dt is a positive 4. So let's go here in our equation and put a 4 here. All right? And they tell us, it starts in the top right here, x is decreasing at a constant rate of 1 unit per minute. If it's decreasing, it should be negative. So dx dt is -1. We will put that as our last value here. And let's simplify this. Okay, we don't get a calculator, but don't freak out. 6 squared is 36. 36 times 4 is 24. Okay, that's 144. Plus, okay, 20 times 12 is 240. But then I got to multiply that times a -1, so -240. All right, and if I combine those, oh my God, if I take away that, what's that, -96? There you go. So the answer to the first one that we're doing today, number 21, is -96. All right, that was nice. That was easy. You just got to use the product rule. And remember that for related rates, we need to write dy dt if we're taking the derivative of y, or dx dt if we're taking the derivative of x. Done. 22. Let f be the function defined by f of x equals 2x cubed minus 3x squared minus 12x plus 18. On which of the following intervals is the graph both? Okay, we're finding two things here. Decreasing, that means my first derivative is negative or less than 0. And concave up, that means my second derivative is positive or greater than 0. So I got to find both of those things. All right, first derivative. First derivative of f is, looking at the equation they gave me, that's 6x squared minus 6x minus 12. Let's find out where that's equal to 0 first so we can figure out our critical points. Well, I'm going to divide everything by 6 just to make it really easy. So I've got x squared minus x minus 3 equals 0. I'm missing something. 6, no, I got it. That's a 2. Duh. I'll be okay. That's a 2. So I've got x minus 2 times x plus 1 when I factor it. Get a little bit more room here. And if I solve this, I get x equals 2 and x equals -1. I'm going to put that on a number line. There's my number line. Here's where x is -1. Here's where x is 2. The value of my first derivative is 0 at both of those places. I need to check spots in between. Okay? So let's check x value of 0, an x value of 3, and an x value of -2. And I'm going to put them all into my first derivative. Okay? Which means I could put them here, or I could put them here, which is probably what I'll do, because I don't care about the actual number I get, just the sign I get. All right, let's try 3 first. If I throw a 3 into this x, I get a +1. If I throw a 3 into the x with a +1, I get 4. So a positive times a positive would give me positive values here for the first derivative. Right? Let's try 0. If I throw a 0 into this x, I get -2. If I throw a 0 into this x, I get a +1. A negative times a positive means all of these are negative. Let's try our -2, last but not least. -2 minus 2 is -4. And -2 plus 1 is -1. A negative times a negative gives me a positive value. So, again, we only care when our first derivative is negative, okay? And that only happens between these 2 points, between -1 and 2. They're all negative, all right? So I'm just going to make that little note. This right here happens between -1 and 2, okay? But I also need to figure out when my second derivative is positive. Let's not forget, we just figured out this part here, but I still need the concave up. So now what do? I need the second derivative. And I do the same thing. I'm going to take Okay, this right here is the first derivative. Let me highlight that. I've been trying to avoid using the yellow because it's tough to see in the video sometimes. Here's the first derivative that I just highlighted in green. And now I need to take the derivative of that. That's 12x minus 6. All right, I want to figure out where that's equal to 0 because that's going to give me my points of inflection. Okay, again, let's divide 6 out of both of these. I get 2x minus 1 equals 0. And that only happens when x is 1/2. Okay, I can add 1 and divide by 2 and prove that, but I shouldn't have to at this point. Number line time. And I know for a fact that when x is 1/2, my second derivative is equal to 0. All right, let's check some numbers on both sides. Oh, this is great. 0 and 1. Fantastic. And I am going to put them into the second derivative. I can do this. Oh, I can do this. Don't matter. Green, let's take -1, or +1, I'm sorry, and put it in for this x. Okay, 2 times 1 is 2 minus 1. 2 minus 1, that's a positive value. So these are where it's all positive. All right. And if I throw in a 0, that goes by it's -1, so these are negative. They want to know where I'm concave up. I'm concave up anytime I'm bigger than 1/2. So let's write that down. To this one, when x is greater than 1/2. Okay, so somehow I've got to kind of mesh those two intervals together. All right? Let's do it. Sometimes it's easier to visualize on one number line. All right? My first derivative between -1 and 2. This is what I'm looking for when it's negative. All right? My second derivative at 1/2, I'm looking for when it's positive. Positive up here. All right? The first derivative is positive here, just to give you a visual. And my second derivative, which I'm putting above the first derivative, it's negative here. All right, so where, and this is my x value down here, okay, that to me is a lot easier to see. Where is my second derivative, and I'm going to use the yellow highlighter, positive, and my first derivative, negative. So right where these two overlap, here, okay, in that section. So I'm going to say when x is between 1/2 and 2. Okay, so between 1/2 and 2. That's my answer right there. 1/2 and 2, that's choice D. Very good, very good, very good. All right, I think we finally got one that's not going to take forever. 23. If f is the function defined above, and they give us a nice piecewise function, then f prime of -1 is. All right, derivatives are a lot like limits to where both sides need to be the same. So I need to find the derivative when x is -1 of the top part of my piecewise function, and the derivative when f is -1 of the bottom part. All right, well, let's start. F prime, now this is when x is less than -1. F prime of x is, well, that's just 3. The derivative of that is 3. All right? Bottom. So what about when x is greater than or equal to -1? The derivative, okay, that's -2x, and I want that when x is -1. -2 times -1, that's 2. Guess what? 3 does not equal 2. So just like limits, if they're not equal from both sides, it is non-existent. So what's the thing to take away and put that in your cap or in your back pocket? That derivatives for piecewise functions are like limits. They got to be the same for both sides. Number 24, let f be the function defined by f of x equals 3x plus 8 times 5 minus 4x, all over 2x plus 1 squared. Which of the following is a horizontal asymptote to the graph of f? Oh, it's another easy one. In order to find horizontal asymptotes, okay, we need to take the limits as x approaches positive or negative infinity of our function of f of x. And whatever that equals is our horizontal asymptote. Well, how do we do that? Well, we take the biggest term in the top and the biggest term in the bottom. Now, if I take the biggest term in the top and bottom, I really don't have it written out in standard form yet because I got to multiply these things together. But here's the whole kit and caboodle, I should say. I'm going to rewrite this. Okay. All right. And now, if I were to FOIL the top, the biggest term I would have would be when I multiplied my 3x times negative 4x. That would be negative 12x squared. Everything else would either have a power of x to the 1 or no x at all. So that would be the biggest term. And if I actually squared the bottom, 2x plus 1 times 2x plus 1, my biggest term would be 4x squared. So those are the two biggest terms, the biggest term in the top and the biggest term in the bottom. Now I try and simplify, if I can, before I plug in an infinity. X squareds go away. 12 divided by 4, which is negative, would be 3. And horizontal asymptotes at y equals negative 3. Boom. Another easy one. Number 25. If y equals x squared minus 2 and u equals 2x plus 1, then dy du equals. This is a really rare problem, but just put the derivative of y over the derivative of u. All right, well, the derivative of y, which is this one here, is 2x plus 1. Or excuse me, that's a 2. And the derivative of u is just 2. I mean, and if you look and you're like, oh, I don't see that as an answer, I can simplify that. I can take a 2 out of everything. This becomes a 1. This becomes a 1. This becomes a 1. So I really have x plus 1 over 1, which is x plus 1. All right? And if I'm looking, I made a plus where there's a minus. Haha. This should have been a minus, which means this is a minus, which means this is a minus, which means this is a minus. Boom. Choice D. Number 26. For any x greater than 0, take the derivative of the integration of 1 to radical x of 1 over 1 plus t squared dt. Whenever I am taking the derivative of an integral, they kind of cancel. Okay? And my upper bound gets put into whatever variable I have, in this case, t. So I have 1 over 1 plus the square root of x, that was my t, but don't forget that has to be squared, times the derivative of whatever the square root of t is. Chain rule. Okay, so the square root of x, I said the square root of t, but we'll call the square root of x, that's the same as x to the 1/2. And the derivative of that, the 1/2 comes down here. I subtract 1, that's negative 1/2. Which means, to make that positive, I'm going to put that in the bottom. 1 over 2x, the positive 1/2. And for the sake of our problem, let's turn that back into a square root, because that's what our answers are. 1 over 2 square root of x. This is the derivative of that. Okay, so times 1 over 2 square root of x. Let's clean this up. All right, well, square roots and squares cancel. So the tops, 1 times 1 is 1. I'll put this out front, times this part right here, which is now 1 plus x. All right, that looks like it's an answer, and that looks like it is choice A. Not too bad. Not too bad at all. 27. A particle moves on the x-axis so that at any time t is in between 0 and 1 inclusive. Its position is given by x of t equals sine of 2 pi t plus 2 pi t. For what value of t is the particle at rest? At rest means the velocity is equal to 0. So let's first take the derivative of position. That will give us velocity. Derivative of sine is cosine. This inside stays the same times the derivative of the inside, chain rule. That's 2 pi, all right? Plus the derivative of this thing, which is also 2 pi. All right. Now, I want this. This is velocity now. Well, if we want to know when the particle's at rest, we want to know the velocity at, find what value of t. Yeah, we want to find when the velocity, not just time, is 0. We want to figure out the t that makes that happen. Okay, so I have, I'm going to rewrite this, 2 pi t times 2 pi plus 2 pi. Let's just start doing some basic algebra, shall we? Subtract 2 pi from both sides. Cosine of 2 pi t times 2 pi equals negative 2 pi. All right. Well, if you look, and I'm going to try not to go too fast. If you look at our answers, there's no pi in there. Weird. Well, look what happens when I do right here. I'm going to divide both sides by 2 pi to get rid of this. And if I divide this by 2 pi, that becomes negative 1. Cosine of 2 pi t. All right, well, know your trigonometry. What degree should I have of cosine where it would equal negative 1? That's 180 degrees, or just pi. So in here, we need to make sure whatever we are taking the cosine of, it's equal to pi. So I'm going to take this out, and I'm just going to say, well, 2 pi t needs to equal 180, or just pi. All right, well, let's divide both sides by 2 pi. That will give me my t alone. So t equals pi over 2 pi. And if these cancel, that leaves me just a 1. 1/2. And that works out very well because they're saying my time needs to be in between 0 and 1. And that's choice D, which is 1/2. Look at us go. Proud. Pretty proud of us. Scroll down so you can see that. Pretty proud of us. All right, last one, number 28. I have the options listed to the left, A through E, and I have the problem to the right. So if you're looking at this kind of confused, I don't know why I didn't put the problem to the left and the multiple choice to the right, but we have what we have here, kids. 28. Shown above is a slope field for which of the following differential equations? So this slope field over here should represent one of these. And what jumps out to me immediately is the horizontal lines. You'll notice, and I'm going to highlight these are all horizontal. And also, these are all horizontal as well. Okay, so anytime, let's figure this out. The y-axis, that's when x equals 0. So anytime x equals 0, these derivatives or slopes should be 0. All right? And this one right here, I mean, I can kind of guess if this, and I mean, that's maybe 1, maybe. So that's maybe where y equals 1. It's going to be somewhere around there, okay? So A, B, C, or D, or E, should have a slope of 0, because that's what these horizontal lines mean. At y equals 1, my slope, or I should write dy dx equals 0. And at x equals 0, my slope, or derivative, should also be 0. So let's take a look at this first one. When x is 0, well, that's 0 times y minus another x, which is 0. 0 minus, that does equal 0. That's good. What about when y is 1? Okay, let's check when y is 1. Okay, this is when y is 1. So we got x times y, which is 1, minus x. So that's x minus x, which is also 0. Boom. We didn't even have to check the other ones. That's perfect. That is absolutely perfect. When x is 0, choice A results with a derivative or slope of 0. When y is 1, choice A, the derivative or slope, is also 0. That's exactly what I wanted to do. And we're done. We are done. That wasn't so bad. Those first couple of problems took a little bit. Maybe I explained a little too much. Who knows? But we are done. The rest of these we kind of ripped through. Nice. Like the video, ring the bell, leave a comment if there's something you want to see. Follow me because that's how you get notifications that I put up new videos. Okay? Have a good day. And I will see you on part 2 when we finally get to use that sweet, sweet calculator. Bye-bye.
Don't forget to subscribe and ring that bell.